Hi, my name is Tom Manning, and I'm a chemistry professor at Valdosta State University. I'm going to give a quick overview on our new composition for delivering antibiotics for different forms of TB. It's a biodegradable carrier aimed at inhalation, and kind of the novel aspect of it is that there's a host of species in there, 10 or 12, that bring additional biological and chemical activity. Okay, so this is kind of a quick overview. Here's our particle, and inside I'll start from the upper left. Right, there's 3 amino acids, branched amino acids. There's cholesterol, that is second to stearic acid in terms of the total mass. Copper stearate, stearate C18, vitamin C or absorbic acid. Stearic acid is our main composition. Right, typically it's over 50% of the total mass. There is a copper, sucrose, glucose, EDTA complex. There is the antibiotic. These are existing antibiotics. We've already published papers and received a patent on taking an existing antibiotic that no longer works and making it work again or work better by packaging it in a certain way. So we hope to have the same results here. PEG is used as a protectorant. We have sodium acetate in there. There's oleic acid. It's an unsaturated fatty acid, and we'll talk about that. And then there's sodium chloride, the strong electrolyte. Okay, so what we're doing is not just having a single species or a single antibiotic, but we're having multiple things that either enhance the antibiotic through some sort of chemical or biological process, or they have their own mechanism of action. So for example, some of them will bring bacteriostatic or bactericidal activity. Some serve as an energy source for the bacteria. A couple of the things that we're adding are components of the cell membrane, which means we hope to have a Trojan horse effect where it brings in the various species as it's building up the membrane. We're enhancing existing toxic species, and we'll explain that as we go through. We're generating reactive oxidation species, ROS. These are things like hydrogen peroxide and hydroxy radical. Some will randomly bind proteins inside the TB, make them either shut down or not work properly. In some cases, you'll see that we try to match the polarity of our complex to that of the outer membrane of the TB, nonpolar and nonpolar, so there's a selectivity there based on polarity. And then we want to protect or prevent certain reactions from happening until they reach the proper destination. Okay, so the major composition that we selected is stearic acid, and that's anywhere from up to 75% by mass, and you'll see we'll have some formulations towards the end. I should point out that stearic acid, as well as other fatty acids, are part of the cell membrane of Mycobacterium tuberculosis. So this adds an element of it being taken into the bacteria, even if it's at the surface, and along with it, it will bring some of the other species with it. It's kind of a Trojan horse effect. There will be, it also serves as a nutrient for Mycobacterium tuberculosis. Right, it gets ground up into acetate in some of the cycles. The aggregate or the small particles that we're using should be viewed as cellular debris by macrophages, alveoli macrophages in the lungs, so it's being inhaled in the lungs. Small, tiny, 30 to 50 nanometer sized particles that the macrophage will uptake, and then once inside the macrophage will attack the TB. Solid stearic acid is solid, and it contains the other components. There are smaller fatty acids that could be considered, but typically they're solid. They dissolve much faster, or they're already a liquid. And so stearic acid has a pretty low solubility in water, which is what we want. So that way it dissolves slowly over weeks or months. And you'll see that there's some additives that we put in that can regulate the dissolution rate. Okay, so the basic idea with using nanoparticles is to reduce the dosage of the drug and to reduce how many times it's actually given. Okay, so considering that roughly 90% of all TB patients, particularly latent TB, it's in their lungs, that this is aimed at that particular scenario. And so this is inhaled, like this, the nanoparticles are small enough that they could be within aerosol, many nanoparticles within aerosol droplets. And maybe it's given, a couple times a week as opposed to daily tablets. And then once inside the lungs, we make them small enough so that the macrophage can not only ingest it, but we don't want them to be too big. Like say, we don't want them to be 300 or 400 nanometers, because then they might deliver too much of the drugs to the macrophage and also kill the macrophage. We'd like to keep the particles small enough to knock out the TB, inhibit the TB, but not damage the macrophage. Okay, so one of the things that we include, this is kind of the one inert thing, is sodium chloride. Right? It's a strong electrolyte. It dissolves easily in water. That's added to impact the dissolution rate of the stearic acid. So the more sodium chloride you have in there, the faster the stearic acid will, or the stearic acid composition will dissolve. We include PEG. So PEG is an inert polymer, but we use it to protect two species in particular, absorbic acid and copper-2. Both of those can undergo oxidation or reduction reactions, and they might stick to things that we don't want right away. And so by using PEG, as well as a couple of other things that we're using it as a protectorate, we have used PEG as a protectorate in the past. We've published some papers on it. We've also received a patent that revolves around PEG being one of 4 components of taking an existing antibiotic that no longer works and making it work against drug-resistant TB. So PEG is well known in the medicinal or pharmaceutical formulation community, but we're using it more as a protectorant against oxidation reduction than as just kind of a filler. Cholesterol is our number 2 additive in terms of mass behind the stearic acid. And so this also is used as an excipient in formulations, but our use is kind of unique in that it is a significant nutrient source for TB, particularly in a latent form. And so by adding the cholesterol, we're going to accelerate or start some cellular processes that should help in the uptake of the drug into the TB once the aggregate or the nanoparticle containing stearic acid is ingested into the macrophage. And I'll leave it to some of the references that we're putting at the bottom to go into more detail. But cholesterol is, inexpensive. It's relatively inert in the body at the levels that we're going to deliver it. But it does open up some doors for us to make the delivery of other drugs or other species more efficient. Okay, so copper is well known to have a fairly high toxicity against TB in different forms, drug-resistant TB. But one of the things that we've learned that you have to do with it is protect it from unwanted oxidation or reduction reactions, as well as binding to proteins. So what we do is it's attached to EDTA, a well-known chelating agent. It's then encased in a matrix of glucose and sucrose. Sucrose is a non-reducing sugar, so it helps reduce any kind of reactivity with the glucose. And glucose, monosaccharide, is a key source of energy. So by placing that there with the TB, we hope that this nanoparticle within the stearic acid matrix is digested, and then the copper comes out and it wreaks havoc. I should point out that in addition to generating reactive oxidation species, right, copper-2 can generate hydroxide, hydroxy radicals. There's a host of them that can cause damage. It can also bind proteins, so and any protein, with a preference towards binding nitrogens and sulfides. And so it can cause proteins within the TB to stop working once that aggregate is digested. Okay, we also include zinc stearate and copper stearate. Copper's still in there for the same reason that we already mentioned. And rather than just using EDTA to protect it, we're using a stearate to protect it. Zinc is also included as an essential nutrient that sometimes can be in short supply in Mycobacterium tuberculosis. It also adds a solubility, a little bit more solubility to the stearate compared to just pure stearic acid. So we can regulate solubility a little bit with the zinc stearate, as well as we already talked about with the sodium chloride. Absorbic acid, vitamin C, interesting species. There's been a number of papers published about its use directly impacting TB and about being given with other drugs, known antibiotics, and enhancing their activity. If you take it as a tablet, and it goes through your digestive tract, there's 2 inefficiencies involved in that. One is that it has to go through your digestive tract, it has to penetrate the intestinal membrane, then it has to end up at a specific location right in your lungs. And so the efficiency of that is going to be fairly low. The second part of it is that absorbic acid likes to undergo oxidation and reduction reactions with a host of organic species as well as some inorganic. So it may be that once even though there's an efficiency of getting it there, it will also react in the body before it gets there. So by placing it in a PEG wraparound or a PEG cage, polyethylene glycol cage, and having an steric which is being consumed by the macrophage, the efficiency of using absorbic acid should increase dramatically. Oleic acid is well known as a unsaturated fatty acid, but it also has a toxicity against different forms of Mycobacterium. You can see there's a chart there, and there's a reference at the bottom that will give more detail. So oleic acid is our primary target right now. Our secondary one is linoleic, right, which also has a toxicity. It's actually a little bit more than oleic, but at a slightly different pH. So these are, oleic is a liquid at room temperature and room pressure. So it would only be added at low percent, 1-2%, something like that. And it's not by itself going to be toxic to the TV in terms of knocking it out, but it should be considered almost an irritant that weakens the immune system and allows some of the other species to work better. Okay, so sodium acetate is being added for two reasons. One is we can regulate how much steric acid gets converted to sterate, right? And sterate has a slightly higher water solubility than steric acid, right, with that carboxylate. So sodium sterate's a strong electrolyte. So this can regulate the dissolution rate of the nanoparticles. And that's just a simple acid-base reaction. Okay, and then the second one is, and I'll leave it to the reference there to go into more detail, but acetate is a product of a host of cellular processes in MTB, and by adding additional acetate, we think that it's a Le Chatillier's principle type situation. When you add acetate, it's going to slow those processes down and lead to some toxicity. Okay, the branched chain amino acids, right, there's 3 of them. These, again, I'll leave it to references to go into more detail, but these, by adding it, can add additional toxicity or stress out the system by blocking certain cycles from going. They are inexpensive, and so these we'd add at, you know, perhaps a total of 1-2% between the 3 of them. Okay, so what I'm going to do is suggest some formulations related to this for latent, active, and resistant TB. The masses that we give are ratios, not actual doses. I would assume that when we do calculations on an inhalation dose compared to a tablet dose, right, it depends upon some of the assumptions that you make, but the dose could be anywhere from 50 to 500 times less, for example, for latent TB. In large part because you're putting things right there, right where the macrophages are that are infected with TB, and the species, since they're not going through your body, being distributed everywhere immediately, that they are not reacting, right? So for example, isoniazid is a prodrug. It can react with different things before it gets to the spot, and then that would sidetrack it. So for example, this is a formulation for latent TB. And we drew the fact that it's just isoniazid from the recommendations made by the CDC that you can see on the right side there. Okay, so this would have steric acid as your major composition with the isoniazid built in, and then you have your various species. A key component with this, one of the that you may not see immediately, but if you had just copper and isoniazid, they actually react together fairly rigorously. So the copper plus 2 goes to copper 0. And that happens fairly quickly. So by protecting it with the EDTA and the PEG cage until it gets into the MTB, you're not only preventing copper from reacting with just random species in the urine serum or in the lungs, you're also preventing it from reacting with some of the other species there. Okay, so this is for active TB, and again, if you look at the CDC recommendations, right, there are 4, there's one particular recommendation that we just used as an example. The first one has 4 antibiotics in it, Brif, isoniazid, and then the other 2. And then you go down, you see we have the same type of bioactive ingredients in there with the steric acid. and stearic acid is the bulk material. And then on the right side, when it goes to the second phase of the same recommendation, right, it reduces to 2 of the antibiotics. And then again, with the various other species present. And so again, this, just a thought, right, we don't have any in vivo data to back it up, is that because you're delivering this much more efficiently, that the dosage is going to go down and the number of doses is going to go down quite a bit. And so here's 2 different examples for drug-resistant forms of TB. On the left, in that small paragraph, you can see that it's a quick summary of an FDA-approved treatment that involves bedoquolin and then 2 other species. And then we had the one that we came up with that has the same ratio in terms of molar masses or the molarity that would be, or the number of moles for the 3 different antibiotics. Right? And these have, particularly bedoquolin, have a reputation for having terrible side effects. So by reducing the dose and the number of times it has to be taken, right, it should reduce the side effects. It also would, I think, reduce the price of the drug, since some of these, in the American market at least, are fairly expensive. And again, we have our other species there to enhance it. On the right side, there's also a formulation, the link's on the bottom, for just bedoquolin treating different forms of drug-resistant TB. And so that's a formulation that would take place for that. And again, stearic acid has a melting point of about 70 degrees C. And so how we do this can vary a little bit, but we heat it up till it's a liquid, we add our materials, and then we put it at a low temperature to freeze it very, very rapidly, and then it gets ground. We've done some work with making it into actually micron-sized particles. Our lab can't make nanoparticles, but making that into particles. Okay, so a quick review, right? There are a host of species that we've identified that help the antibiotic work against different forms of TB. And each one of them has a role, right? They typically help in a formation of an aggregate or a micelle as this particle falls apart. This particle should be recognized as cellular debris by a macrophage. There's also some in the lungs that will make it into the serum, so it will circulate around the body. These may stick around for days or a week or 2 at a small size, and that again is going to be size dependent, and then how much sodium chloride or sodium acetate we have in there. PEG is used to protect oxidation and reduction reactions from happening until it's on site. And then the other species have the different accelerate cellular processes, right, such as their branched amino acids, acetate, and that can help us in terms of uptaking the drug faster. And cholesterol is an essential nutrient. It's also a common additive for some medications, but we're using it because of its bioactivity. And if there are any questions, I'd be happy to ask for them. This is a quick summary. We can provide references and go into some of the details and some of the thoughts on different species. Thank you.